A very good afternoon to all dear participants. Myself, Dr. Abhishek, and I am going to deliver a lecture on application of geospatial technology in droughts. As we are on fourth day on the special our DLP course, which is on climate change induced disasters, and in the same lecture series, I am dealing with like as agriculture drought more specifically. So I am dealing that particular topic and give you the detailed information about this particular topic. So start from the background of the topic named the drought. As you already have or may have that participants have the substantial idea about the drought with respect to its definitions. So but my point of concern here, so that what's the importance of these topics, what are the important background that I have to very first confer with you. Then we follow up that few fundamental part and come to the part of geospatial technology, how we can use it for the assessment of actual drought and monitoring part. So very first, if I define the damage part, if you simply name the way what kind of different natural disasters are there, like if you just name it like landslide is there, volcano eruptions is there, flood is there, drought is there. So out of all kind subsidence is there, all kind of natural disasters. If you confirm with the same, the drought more specifically is one of the most damaging and costly natural disaster at the global scale, not only in terms of you can say it's money, but also as the number of people in terms of every year millions of people are affected because of that particular natural disasters. And in case of economy part, if in generalize we assess a tentative or a rough figure of its related economic loss, so that is around $6 to $8 billion economic loss each year because of the only and only drought. When you come to the part of onset and prediction of the drought, which is little bit complex to understand, but when we very first define how we can consider or how we can say it's a onset of drought. So I just give you example which may give you a more clear picture about this onset of the drought process. If let's assume I am a farmer and I am doing a crop cultivations in kharif season or monsoon season in my farm, a roughly in date of 15th of or 20th of June. If the same week or just prior of 1 week or that at the crop sowing time, if the rain was there in my field, so okay, that rain may you can say recharge my soil with respect to its moisture status. So there is a certain residual soil moisture in my soil or my field. So on the basis, I simply do the crop cultivations or you can say the sowing applications. But just after you can say that I'm after you can say a 3 day or 5 day and so on period, I simply expect there may be a rain on my field. If the rain may not be there for next you can say 3 days, 5 days, 7 days, which I am expecting. If rain may be there, the conditions may be normal. That is always on a positive side. But if the rain may not be there in next 7 days, so what's the situation in my farm? There may be chances of mortality of the young seedlings, and if that dryness or inability of rainfall may prolong for next 2 week or 3 week, there may be higher chances of a severe mortality of my seedlings in my field, and same time there may be chances of you can say a complete crop failure or you can say resowing applications which may be required at my farm itself. So and the same time, if I define what is the onset of the drought, that was although started with the last date of rainfall, which may be 15th or 20th of around, you can say the rainfall which was received at my farm. So it means how you can decide the date of the drought, which was onset on my field, which was you can say prior 2 week, which already happened. So if I'm saying the onset part is complex to define, then how we can say about the prediction and prediction with a certain accuracy, because the prediction nowadays people are also working with machine learning, AI, ML tool part also, but there is a substantial gap in terms of its accuracy part and sensitivity analysis of the model. So the prediction is also a complex things which has to be done for any area specific, and because it is most difficult to observe with the naked eye and at the same time forecast in quite well. And when we're talking about with respect to our Indian perspective, India as a agricultural country, the incidence of drought, which is a recurring phenomenon, number of area or region in India, which is a regional to localized scale. So come to the part of straightforward the definitions. Although you have or most of the people have idea like with respect to lack of moisture conditions, lack of water availability, lack of rainfall, maybe a situation of drought, and that define your drought phenomena. but these are scientific definitions or technical definition which give you a more detailed idea about this particular definition and phenomena, which is mentioned here and which is defined in Glossary of Meteorology in 1959, which define a period of abnormal dry weather sufficiently prolonged. A period of abnormally dry, it means there should be a certain period. We can't say for with 1 day, 2 day or 3 day or of you can say zero rainfall period, or we can say it's a condition of the drought. There is substantial period duration on time which is based on the dry spell. So based on the dry spell is defined what is the situation of the drought, and that you can say deficiency of water which may be create in situation as abnormal dry weather conditions. Abnormal, it means a area which is although classified as a excessive arid condition or semi-arid condition, which is not at all as considered as a normally you can say wet or a it's although you can say normally dry conditions are there. So when we talking about the dry drought condition, which should be for a abnormal dry weather conditions or a region specific only, and that dryness which may be sufficiently prolonged, which may create a situation of serious hydrological imbalance in the affected area, and that should be only and only with respect to affected area. So we can say drought is a localized phenomena, a region specific phenomena, where that you can say the deficiency of water which may create a serious hydrological imbalance in the particular area, or lack of water conditions may significantly impact on you can say that area specific water conditions, water availability, which create a situation in abnormal dry weather conditions only. So that's defined a more clear in technical manner about this definition part. Come to the part of the drought in that same its introduction, like drought which is a silent threat to Indian rural economy, where we can say around our 50 to 55% of population directly or indirectly dependent on agriculture. And if I'm saying the total Indian rural populations, that is around 75% of our Indian rural populations are dependent directly and indirectly on agriculture activity. So agriculture is a very immediate or you can say prime victim of the drought. And there is also number of consequences of the this drought phenomena, which there may be situations of unemployment, more unemployment in rural area. There's more on you can say higher rate of cattle starvation conditions, fodder shortage condition, and along with this there is a, in case of our non-agriculture impact, there is a shortage of drinking water, because if water may not be available in farm or in number of area specific, so definitely there may be you can say there net significantly reduction in the surface, subsurface and the groundwater recharge, and that may create a situation of the water drinking. And recently, as you heard about number of news in the parts of our India where you can say because of the inability of rainfall, the drinking water limitations may rise over the time. Then what are the major causes of the drought? As I enlisted few of the points, like very first and important was the erratic behavior of monsoon. That as we know about that with respect to our Indian monsoon condition, the southwest monsoon is the prime monsoon, which may cover up around 75 to 80% our pan India level geographical area, and that monsoon, that particular southwest monsoon, may simply recharge our surface or groundwater for the same, and also significantly used in the crop cultivations. And if that monsoon may behave erratically in terms of its availability part and its intensity, its time and availability, so it's drastically or significantly impact on the crop growth as well as its survival in number of area specific. Along with this, the ocean atmospheric circulation disturbance, more specific also, which defined as a El Nino southern oscillation phenomena. El Nino, as recently in the news, that term which is there, which defined like this year is a severe El Nino year, which may significantly impact on the water availability through the form of our, you can say, abrupt monsoon pattern with the same year specific. So that is also a major cause of the drought. Along with this, the rapid depletion in the forest cover, soil moisture level, you can say unavailability of the water, same time, then timing of the water supply in the irrigation frequency, excessive use of surface and groundwater. These all are cause of the drought. Like in case of specifically the last point, like which we can define as in manner, like a farm which has a groundwater, maybe in form of you can say open well or dug well, which have the water availability status or water availability conditions for a one irrigation or two irrigations. But because of you can say abnormal hitting a very initial phase of the crop growing time in the same monsoon period, if the farmers use that particular one time and two time irrigation from its dug well or its groundwater, so that same farm may not have the now the next irrigation for their farm, for their crop, And in due course of time of the crop growth at the particular season in monsoon period, if water required in that farm because of unavailability or erratic pattern of the rainfall, then we also can say, like at the time if water is may not be available, so definitely it's create a situation of the drought. So that is also a major cause of drought as enlisted here. Come to the part of the impact of the drought. There is a number of impacts are there. Majorly few of the points I mentioned here as a highlighted. Like very first is the shortage of food productions due to the failure of the crops, which may drastically impact on that crop production in area by area, and which may be predominant with respect to area specific crop productions. Then shortage of the drinking water and the fodder for the livestock, that is also a major impact. Then decrease in animal population, deforestation due to unavailability and fuel and agriculture waste. So number of impacts of droughts are there which are easily visible with our eye in a number of parts of our Indian region. Now come to the part of the types of drought. There is a total 5 types of droughts are there, which is based on the rainfall availability and which may impact on that other living organism in number of areas specific. So like very first, if I classify or define it in as per the classification, that meteorological drought, the meteorological drought when then actual rainfall is significantly less than 25% and more for over a wider area, then we'd say it's a meteorological drought. When talking the hydrological drought, there's a marked depletion in the surface and subsurface water. It means if the dryness may prolong for a longer period, then there's a situation. So like when your surface water as well as your groundwater may not be recharged, and there will be consequently a dry up of your lake, reservoir and rivers are clearly visible. In case of agriculture drought, there is a specific definitions which define the inadequate water availability of the crop due to imbalance of your soil moisture and crop nutrition in the farm. How we can say it's a situations like in generalized, like plant are doing that evapotranspiration, and the plant because of the evapotranspiration that you can say the photosynthesis process is associated and attached with the same. If plant is regularly doing the photosynthesis, evapotranspiration process is in normal state. If the water may not be there in the form of soil moisture or residual soil moisture, so plant may not take up the water and may not perform that photosynthesis activity in normal manner or evapotranspiration process also. So there is a you can say substantial impact on the crop growth side because of that you can say reduction in the photosynthesis process. So if I'm saying as it is mentioned the definition, like due to imbalance between soil moisture and crop evapotranspiration, there the situations may create which define as a agriculture drought. Along with this, there's two more types of droughts are there. Like in very first is the ecological drought, which define as like if any area which has a lack of soil moisture or the groundwater, or you can say may not be recharged because of the unavailability of the rainfall, there may be chances of ecological damage in the particular area specific also. Like there is a number of area of Ramsar area or wetland area, mangrove area. If the water may not be available in the form of the rainfall, so the surface water may not be available at the farm at their locations or at the you can say ecosystem. If the water may not be available, the flora and fauna, their population, their growth is significantly affected, and that is situations of ecological damage in the particular area. So this type of situations we call it say ecological drought. And also like the water unavailability in because of erratic behavior of monsoon or unavailability of rainfall, it's not only impact the water status or meteorological conditions or agriculture, but also it's uh, you can say markedly impact on the ecosystem or you can say ecological status of number of area specific. So that is classified as a ecological drought. Now in recent decades, number of you can say researchers, they are also working on the ecological drought part also for their regular assessment and monitoring. Then there is a one more type of drought which is a socio-economic drought, and this is a special kind of drought which defined when the demand of any economic good that exceed from the supply. So as a result, the weather related shortfall in a water supply. So that situation also because of the imbalance between the demand and supply of any economic good, which may also create a situation of a socio-economic drought in a number of region specific as a localized part. This is another type of classification of drought which is based on the time of occurrence. There is a total 5 type of droughts are there as it's enlisted here, that is early season drought, mid season drought, late season drought, apparent drought and permanent drought. If the drought conditions, if you can say deficiency of water may come in the early season, or you can say start of the season, so it may significantly impact the part of germinations. If the conditions may you can say increase in, you can say, for up to fortnight level or more than that period, so there may be chances of higher side of mortality, or maybe the resowing of the particular resowing of the crop in the particular area or field specific. In case of mid-season drought, if the water may not be available when the plant on the stage of peak vegetative crop growing conditions, and also from the transformations from peak vegetative to reproductive phase, if the water may not be available, there also be significantly impact on, you can say, crop yield part also. Then there is a late season or terminal drought. If the water may not be available at the time of the maturity and the final, you can say, when the grain attain its proper size. So if the conditions may prevail for a longer period, so this may impact on qualitative as well as the quantitative status of the crop. So because of the unavailability of water, the grain or that particular, maybe you can say, the seed may not attain its proper size and may not be have the proper tone, texture, color, so which also deteriorates quality attributes and significantly impact on its price part also. So that impact in terms of at the time of its maturity and the final attaining its size. In case of apparent drought, this is a kind of a special kind of drought when the farmers or any area specific farmers or you can say field are suitable for high crop water requirement crop like paddy or sugarcane, but because of the unavailability of rainfall or water, farmers forcefully cultivate a crop which may be the moderate to low crop water requirement. Like in spite of sugarcane and paddy, they may cultivate maize, soya bean, or maybe pearl millet crop. So then this is a situation called as a apparent drought. Or in case of permanent drought, when a area is although classified as semi-arid to arid region, when the annual rainfall is less than 50 mm, so that area although classified as a permanent drought region, because that length of growing period in the same area is less than 30 days, and which is not suitable at all for even for the short duration crop type also. So this is a drought classification based on time of occurrence. Now come to the part of straightforward, that its evaluation side or its computation side. So the very first I am discussing here the conventional approach by IMD, India Meteorological Department, as they are doing basically this calculation based on the LD anomaly index, which is solely dependent on rainfall data sets, as it is mentioned in this particular slide. Like drought monitoring by IMD doing by calculation of LD anomaly index, and which is on the basis of potential evaporation and actual evaporation. And when the potential evaporation is calculated on the basis of annual formula, and actual evaporation calculated on the basis of the water balance technique. And if the values are on the negative side on or 0, so this is a condition normal or non-arid condition. If the values on positive side, and as it is increasing from the positive side, like it is that aridity conditions may increase, like that if the value is between 1 to 25, the condition defined as a mild arid, then 26 to 50 is defined the moderate arid, and more than 50 value define the severe arid conditions as per the particular classifications. Along with this, there is also one type of indices which is used for assessment of meteorological drought, more specifically, which is also solely dependent on the rainfall data sets. And the name is the SPI, Standardized Precipitation Index. The Standardized Precipitation Index is solely calculated by rainfall data sets, as the formula is given xi minus x bar divided by sigma, where xi define the particular period specific rainfall, x bar define the mean long-term mean rainfall, the sigma define the standard deviation for the particular corresponding period. And as per the SPI value, if the value is above in the positive side or up to minus 0.5, so this is a condition normal, or this is a condition of no drought. As that value is going towards the more and more negative side, the more dryness may define, as per the table is given in the slide, which is defined from abnormal dry to moderate, severe, extreme, or exceptional drought conditions based on that more and more negative value in SPI range. But this all about with the basis of the rainfall data sets, and those rainfall data sets are mainly observed by that rain gauge, that ordinary rain gauge or automatic rain gauge, which are location specific or point specific. So that may also create a situation, or you can say limitations, that you can say understanding to define the spatio-temporal variability of the particular parameters or the conditions of drought in that area specific. So to compensate that particular you can say limitations, or to improve the situation. That's a one solution is there, and that solution is with combination of that monitoring tool like remote sensing or weather informations, which we may give you the spatial temporal informations about that condition, localized conditions. So that integrated with the ground observations that give you the more reliable results or reliable information related to regional to national level drought conditions or drought maps. So here this slide define you the remote sensing of vegetation. More specifically, if I am saying how that spectra may vary with respect to VNIR range, more specifically visible near infrared band, and how a healthy and stressed vegetations define the reflectance. In more specifically, if I am saying or point it out in red band wavelength and NIR wavelength. So in case of your red band wavelength and near infrared band wavelength, there is a drastic variation in case of your healthy and stress vegetation, and that 2 point specific variation in reflectance may ultimately utilize in generation of a specific or different kind of spectral vegetation indices. Like very famous indices, the NDVI, normalized difference vegetation index, and which use as a proxy of crop vigor. If NDVI value is more in the positive side, as it has the range of -1 to +1, so if the value is on the positive side near towards to the +1, so that's define the healthy vegetation, and if the value is close to the 0 side or in you can say in decimal 0.2 0.3, it's kind of situation which define a stress vegetation based on the time stage of the crop. So with that understanding, if you integrate that informations which is derived from the remote sensing at that visible near infrared band and use the spectral vegetation indices, so we can easily assess the condition of the drought and monitor for a larger area in terms of spatio-temporal variability. So come to the part of the number of indices are there, like a very first, as I define here, vegetation condition index, which is based on the NDVI dataset. Basically, it's a normalization of your NDVI datasets where we use long-term or historical NDVI data of the particular area specific, and by using this formula, we can calculate the vegetation condition index. As the formula given, it's NDVI I minus NDVI minimum divided by NDVI max minus NDVI minimum multiplied with 100, where define what is the situation in the last 10 year, 20 year, minimum 10 year, and so last 20 year, 30 year, 40 year, what was the conditions of NDVI maximum and NDVI minimum. On the basis of that, what is the situation of the current time. If the NDVI I condition is near to the maximum side, so your definitely VCI value is close to 100. If the NDVI I or current season NDVI value may be close to the NDVI minimum side, so your VCI value is close to 0. So based on the VCI value, we can further classify it also the drought conditions. Like if the VCI value is higher than 50, it's defined the normal conditions, while the if the VCI value is between 25 to 50 or 35 to 50, that define the moderate drought. And if the value is 0 to 25 or 0 to 35, based on the classification which given by the Kogan and the Patel, so we can utilize it and define the severe drought conditions. So likewise, we can easily classify based on the VCA value. I just give you the example of the same, as we did one study of the Marathwada region for using MODIS 16-day composite data sets. And here you can see that total 15 year, the 12 year so and 3 and so total 15 year of MODIS data sets we analyze for active crop growing period in the monsoon in the Kharif season in July, August and September. So there are total 6 scenes as per each and every year define the active crop growing period of the July, August and September of VCI, which is solely we derive from the NDVI datasets, historical NDVI datasets. Along with this, such kind of analysis also give you idea about, like as you can see in 2002, and there was a late season drought where the more redness or in image, or you can say more severe drought conditions was prevailed in late season, while in 2008 there was early season drought. So like you can say inter-season variability or intra-season variability, which we also encounter with such kind of assessment if you have more temporal resolution based data sets. So such kind of understanding, along with this, that pixel by pixel, you can say raster basis analysis results you have, so you can more, you can say detailed manner analyze the results as well as the spatio-temporal variability of the drought conditions in any area specific. Along with this, based on their mean value or median value, we can define how many years in that particular area or at the district level, block level, or you can say at that sub district level, we can say were severely drought affected or moderately drought affected, or the normal conditions was prevail in the particular area. So such kind of assessment we can do if we have the historical long-term data sets, and using remote sensing give you edge to understand about this phenomena from regional to local scale. Sorry. I directly come to the part of this NADAMS project, which is currently taken care by Ministry of Agriculture and Farmers Welfare. There is a one their center, or uh, which name is Mahanolovis National Crop Forecasting Center (MNCFC), which is situated in the Pusa campus, New Delhi, which is now custodian about this project, and that is projects of on the drought. The name is the NADAMS. NADAMS is the National Agriculture Drought Assessment and Monitoring System, and which was, you can say, developed by NRSC in assessment of agriculture drought with a very near real time information, and where you can say severity level and persistence of agriculture drought at the state level, district level, and sub-district level results are generated. Currently, around 17 states of India are considered under this NADAMS project. When MNCFC carried out that particular kind of assessment using number of, you can say, remote sensing derived informations in the same to do the, you can say, drought assessment for the Kharif as well as the Rabi season. So this is the overall methodology, which is methodology flow chart. It is mentioned in the particular slide, which is in detail defined in new manual of the drought management, which was published in 2016. So Ministry of Agriculture and Farmers Welfare published this particular, with support, or you can say MNCFC, they published this particular manual, and where they define like what is the you can say in agriculture assessment, how we can proceed with respect to rainfall data sets, and further you can say remote sensing based inputs. So based on that, they define the drought trigger conditions 1, and if the condition is set up, then what's the situation of drought trigger 2, and if the drought trigger 2 condition is set up, then what is the further, you can say, step 3, which on the basis of you can finalize determination of the drought in any area specific. In 2019, they also made one amendment in the same drought manual, because till that, like, as they assess the Kharif season only as a drought season, or you can say Kharif season, in Kharif monsoon season or Kharif season, they are practicing that particular drought assessment part. But after the 2019 amendment, because as per the scientific or technical understanding part in the same, like the same your residual moisture which is there in the soil, which is because of that monsoon availability in the Kharif season, ultimately utilized in number of areas, substantial area or parts of India for the Rabi season crop cultivation. So after that, they, as like number of area also, you can say, may be affected if water or a normal rainfall may not be there in the Kharif season. There will be also a situation of the Rabi season drought. So in 2019, as they made amendment and they include the Rabi season also. So after that, like Kharif season and Rabi season both, drought assessment and monitoring are doing by this MNCFC on a regular basis. So what the situation, sorry, what are the particular indicator, what the process or methodology as they are followed. So very first, in regular manner or in regular practice, they are calculating, and they are you can say assessing the mandatory indicators. The what are the mandatory indicators are there? The mandatory indicators are rainfall deviations, or SPI, standard precipitation index, or dry spell. If the conditions are so, like SPI value is more in the negative side, like less than -1, and so, and along with this, if the dry spell condition, yes, if the prolonged dry spell condition is there, so that is the situation of the drought trigger set of conditions. So to assess if the first drought trigger condition is set off, then they further go for a computation or calculation or impact indicators. And what are the metrics of the impact indicators as it is given here? So basically, they are here in the assessing the agriculture part. In agriculture, they are assessing how much area is occupied by crops. So based on the basis of that, what is the potential region where you can say a significantly impact may be there in the crop growth and its development side. So crop area zone, as they consider from the same in the impact indicators. Further, they are using remote sensing derived information, which is VCI or NDVI deviation. So how much VCI variability is there or NDVI variable deviation is there? On the basis, they define what's the situation of the crop and crop growth in the particular area specific. In case in parameter or indicator of the soil moisture, as they use percentage available soil moisture, moisture adequacy index, in case of soil moisture. In case of hydrology, they are using stream flow index, reservoir storage index, soil surface groundwater index, like number of indices and their categorization. Although they mention in their drought manual, which was they as they published 2016, along with this, the detail, like based on their scaling and their class criteria, they define the impact indicators and its level. So what's the intensity of drought? That simply decided based on the impact indicators. So out of like all that impact indicators, if the selected 3 impact indicators in the category of the severe, so then only it's we defined it says severe kind of drought conditions is prevail in that particular region or area. If 2 out of any selected 3 impact indicators in the condition of the moderate or severe, then it's a situation of moderate drought. If the other condition are so, then it's a condition of the normal. With the same, if the drought, if I'm saying the drought conditions may prevail in area and trigger 2 condition will set off in the event of finding the severe or moderate drought condition, then they proceed for the step 3, and which is the final determination of the drought at the stage of you can say ground truthing, or you can say on the basis of they simply doing that number of sample survey in area specific with respect to ground truthing part. So this is all about the you can say basics or and fundamental side, along with this a basic of remote sensing geospatial technology, and what is the government of India MNCFC approach for the assessment of the drought. Now I just come to the part follow up few of the case study for your better understanding in the same, so that you may get an idea how we can execute such kind of studies, such kind of analysis, and that you can also proceed for your area of interest and your as a you can say as a point of or sorry as a part of research as a project also. So very first, as I define here, estimation of the duration of agriculture drought, that we can as you can do also as we did with respect to mod is 16-day composite data sets. So that's why in the formula as we multiply with 16, while the summation of 1 to x or 1 to n or x, the n is basically here define the number of images. In this study, as we used mod is 16-day composite 16 for a one image, which I previously defined in my same presentation, same class. So that particular image I used here for my assessment. But how I can integrate that image? Basically, we convert these all the VCA maps which we derived at the 16 of the per year specific. So we convert these VCA maps in the binary maps. So how we convert it? So basically, as we already have idea, VCI value less than 50 value is in the drought condition from moderate to severe drought, and more than 50 value is in the normal condition. So if the VCI value is higher than 50, we make it 0, and if the VCI value less than 50, we make it 1. It means where is the value is 1, which is denoted the drought conditions, and where is the value of 0, that define a normal condition. So that VCI binary maps we integrated here with a fashion of the same formula and define the drought durations. As you can see with respect to the legend part of this image, so there is a brownish to dark yellow in color. So those area are having are at the time were having more you can say the duration part, the longer duration of the agriculture are the same. In total area, as you can say in generalized from the Marathwada, this is the results of the Marathwada region of Maharashtra. So the western part, more specifically the western part, has the higher side of the drought duration as compared to the eastern part in generalized. Otherwise, more or less, our area, the complete area has a you can say recurrence of drought condition in you can say every alternate year. And so in case of a follow-up of this same study, same analysis with a estimation of frequency of agriculture drought as we did here, like how we can assess the frequency means how frequently the drought may you can say recur in the same area, or you can say recurrence of the drought in the same, as we did with using the same binary VCI data sets, which we integrate of 15-year data set from 2001 to 2015 and analyze with respect to its frequency part and convert this information as the time domain. So as you can see, there is a red in color or yellow in color as per this image of the Marathwada exam of the drought frequency, where you can say red defined 6 to 8 time and the dark yellow defined 8 to 10 times. So it means more or less 6 to 8, you can say every alternate year that area was hit by drought, or maybe you can say moderate to severe drought. Or in case of orange, you can say out of 3, 2 times there was a drought conditions in the same area specific. And where you can say more you can say detailed manner here, because the results are in terms of spatio-temporal basis, raster basis. So even you can get this understanding with at a block level also or group of village level also, like which area has or which area was more affected because of the drought condition, recurrence of drought conditions. As you can easily see, the southwestern part, in general western part, and out of the southwestern part, which include the Bid, Latur, parts of Parbhani which were severely affected because of the drought conditions, and clearly defined in the frequency of agriculture drought. Come to the part of meteorological drought conditions, like as we earlier defined the meteorological drought as we calculated using rainfall data sets, point observation data sets, but that can be also using remote sensing derived rainfall data set. Also, currently number of you can say satellite and their number of satellite reanalysis products are readily available, like CHIPS rainfall data sets is there, ERA 5 data sets are there. Using that, along with this, our Indian IMD data set is also available at the graded scale, that also we can use for SPI calculation. And this study, as we did for the Marathwada region, where you are going to say y-axis define the SPI value, x-axis define that number of block, the name of the number of blocks which we studied at block level for the same drought assessment part. So here in 2002 and 2015, where all the blocks has the more negative value, so you can easily define with the SPI value, we can easily define more negative in SPI. That was the situation of the drought in the same area, and if the value is on the positive SPI, the condition is a normal, which can you easily define in the year of 2007 and 10. There was a normal year because all the blocks has on positive value of SPI. While in case of 2003 and 2009, there was some of the blocks has a positive, some of the blocks has a negative value. So that year was classified as a moderate drought year for the same. So such kind of study also we can formulate for the meteorological drought assessment also. Now come to the part of next study, which is as we did for the combined index based agriculture drought assessment, which we did for the Bundelkhand Uttar Pradesh area. This is a one kind of study which we did for Rabi season drought assessment. As 2019, as I discussed, like 2019 government Ministry of Agriculture Farmers Welfare, they define it like this year onwards, Rabi season drought was also assessed by Government of India or a ministry of, or MNCFC center. So in the same line in 2020 we did this work, and 21 we published this work, and we did this work with area of Bundelkhand, which is also a region where the recurrence of drought is there in on, you can say, on every alternate year that drought may hit different parts of this Bundelkhand region in moderate to severely scale. Along with this, in this particular study, a very first time we integrate more than two type of indices, two type of spectral indices, which can be defined different, you can say, conditions of the crop, different crop growth parameters likewise. So this is the overall methodology as we follow up. So it is not so like these four indices as we took for just for integration part. Each and every parameter has their specific mean for the integration part. As in this particular study, as we use MODIS and DVA, as I already defined, NDVI is a proxy of crop vigor. So based on this indices where we derive this NDVI further in VCI, which is scale of 0 to 100. So vegetation condition index give you the more detailed idea about the vegetation condition of the particular area specific. The next parameter, as we use the LST, that is your land surface temperature, which is from MODIS site, as we derived this temperature condition index from the MODIS LST, because the thermal data sets give the information about the stress conditions. More specifically, if I'm saying the biotic stress or abiotic stress, where you can say water stress condition is there, drought condition is there. So it is a more water stress condition is there. There is significantly change in that temperature condition for the same. So that's why we integrate that particular parameters in the same study. Then the CHIPS rainfall data sets as we utilize here, which is define the rainfall, because rainfall is an important parameter in the same. And the fourth one is the ERA interim soil moisture. At the time we use and derive the soil moisture condition index. And that soil moisture, because in case of Rabi season, half of the crop durations or the crop time, crops simply survive based on the residual soil moisture. So soil moisture is also important parameter to compensate the loss of the water in the form of evapotranspiration, as well as important for that normal photosynthesis activity. So that's why we integrate all those four parameters, and you can say basically, and these all four parameter we integrate through the MCDM approach, that is multi-criteria decision making approach, and where we use AHP analytical helicate process and define their weightage. Which parameter has the more weightage, accordingly we define it, and we integrate that particular you can say weightage and generate the final drought COT map. The weightage in generalize we define based on, you can say, expert advice. We can define based on the literature survey. We can define based on the sample, or you can say the questionnaires from the area specific, which we can fill up, and on the basis we can define the pairwise matrix of the variables or the parameters and define which parameter have more weightage as compared to the another one. So on the basis of that, we can define the consistency ratio and consistency index, and which is also important part of AHP, and that should be less than 10% on 0.1. So when the condition is so, then only your, you can say, weightage is you can say pass through, and we have a clear cut, you can say, pairwise comparison matrix which can be ultimately utilized for you can say drought severity map formations. We did also like a correlation with respect to or comparison with respect to crop yield anomaly of the same area specific in the Rabi season. So field pea and gram was the predominant crop in the same area, so their yield crop yield anomaly also we assess, and we correlate with respect to CDI, the combined drought index value, which is you can say the drought severity map value at the district level. So these all are the AHP derived combined drought index map of that particular area specific, which was the integration of VCI, TCI, PCI and SMCI index. And ultimately, and also we can, as we assess that gram or you can say pea and beans yield anomaly, which with respect to normal year and drought year, as you can see with this particular slide, like in the normal year, the gram yield anomaly and pea and beans yield anomaly for majority all the districts has a positive value, while in case of the drought year, that crop yield anomaly was a negative value. When we correlate that particular crop yield anomaly value with respect to the mean CDI value at the district level of the Bundelkhand region, so as we found, the correlation coefficient value is more than 0.7 up to 0.85 at the higher significant level, as you can see that 5% of the alpha, the level of significance. So you can easily say like that within this assessment, the combined drought index give you the significant results, which has also truly and significantly correlated with the crop yield data sets also. In a line of that, we also did one study with pan India level, and in pan India level, as we integrate three different kind of indices, one is the chips rainfall data sets, another one is the modis NDVI data sets, and third one is the grace TWSI data sets. TWSA data set, that chips rainfall give the information of the rainfall data sets, the modis NDVI give the information, as I prior discussed, the anomaly difference vegetation index value, and the third one, the grace dataset, which is TWSA, that is your terrestrial water storage anomaly datasets. And based on that, we all the three datasets we define three different kind of indices. The three different kind of indices are PCA, that is precipitation condition index, VCA, the vegetation condition index, and TWSACI is the terrestrial water storage anomaly condition index. And when we integrate all the three data sets and generate a AHP based or you can say MCDM AHP based a final combined drought index map, but in the same, because as we did this study for a you can say pan India level, and more specifically the rainfed region, where you can say around in India 120 plus districts are also classified the rainfed region, and prominent for production of maize, sorghum and pearl millet, which is also part of this research in you can say correlation or in say comparison part. So to understand this phenomena, as we define three different kind of scenarios, basically three different kind of scenarios are the three different kind of weightage part in generalize as we define, and where we can say your CI consistency index or consistency ratio value less than 0.1 or 10%, and if we consider the 10% less than 10% of CI value, then only your HP weightage is acceptable. So with respect to these three indices, we integrate three different kind of weightage as we classified as a scenario 1, scenario 2 and scenario 3, and compare the results of the crop yield anomalies also. Along with this, that selection criteria of these three indices was also at the time in our mind as a research objective, like PCI, that chips rainfall or the PCI data sets define the meteorological drought conditions because it's solely dependent with respect to rainfall data sets. So with this we consider the informations of the meteorological drought. Then in case of NDVI, where we further generate the VCI, which may define the condition of the crop vigor or crop growth, and which is a you can say more or less related to the agricultural drought conditions, while the TWSA and TWSA derived the terrestrial water storage anomaly condition index define the hydrological, because hydrology included your surface, subsurface and groundwater status. So TWSACI, the terrestrial water storage anomaly condition, define that soil profile based water status in any area specific, and which is also a remote sensing derived variable. So in understanding of that, like it with a amalgam of these three, like your agriculture drought, meteorological drought, and hydrological drought. We integrated these three in the three different scenario and correlated the crop yield data sets to find out more detailed understanding about the same. This was the overall methodology as we follow up. So here, as you can see, that as we integrate these three data set VCI, PCI, and TWSI at the three different scenarios, scenario 1, 2, 3, and generate CDI maps and correlate, which I define it. So this is the overall methodology as we follow up, and where you can say your CR value, the consistency ratio value, should be less than 0.1 in case of all short of your weightage conditions. So that was the ternary plot we plotted based on, you can say, the final normalization of weightage of PCI, VCI, and TWSSCI in this condition of the scenario 1, 2, and 3, and all times your CR value is less than 0.1. So once we generate this particular kind of you can say this maps, so here you can easily find out the variability in, you can say, drought year and the normal year. The drought, one of the drought year was the 2004 and normal year was 2020. As you can say, variability in the VCA, PC, and TWSI you can easily visible with the spatio-temporal variation or distribution in the three different kind of indices with comparison of their range from 0 to 100 in all three kind of the indices value. And when we integrated all these three type of indices, the PCI, VCI, and TWSSCI, these all are the spatio-temporal distribution of the combined drought index of our selected years, more specifically 2004, 2009 as a drought year, and 2007 and 2020 as, the drought year, and 2007 and 20 was normal year. So easily we can differentiate, like even with the scenario 1, 2, and 3, it's a clearly, you can say, miserable and you can say distribution to define the drought conditions for pan India level, where you can say major parts of our country agricultural landscape was affected because of the drought conditions in 2004, 2009, and while in 2007 and 2020, although the drought conditions was there, but that was limited in a certain area only. Once we correlate this all parameters of your the scenario 1, scenario 2, and scenario 3 with the crops of sorghum, pearl millet, and maize, which was a prominent crop, or you can say rain-fed crop. When we define the rain-fed, it means a area which is solely dependent on rainfall availability, or you can say the crop conditions or crop growth is with respect to only the rain, the water which is available through the form of rain. So we consider only those area where you can say in Andhra Pradesh, Telangana, Karnataka, Tamil Nadu, Maharashtra, Madhya Pradesh, Gujarat, Rajasthan, Haryana, Uttar Pradesh, and Punjab, where you can say these crops are prominently cultivating, and these three crops are mostly, you can say, a crop which are in a class of low crop water requirement: the sorghum, pearl millet, and maize. And when we consider these crop yield data sets and generate the crop yield anomaly based on their detrending practice and correlate at the district level at the three different scenario, these all are the results which we found as a significance level of 5% and define in all three scenarios. So that is a very clear cut picture defined in majority of scenarios. It was significantly correlated in value of that combined drought index with respect to crop yield anomaly data sets. So that give you a very clear understanding, like remote sensing GIS, or you can say geospatial technology, give you a significant result in terms of your spatio-temporal variability for the drought assessment and monitoring part, and it's truly and significantly correlated with crop yield data sets. So yeah, this is all about from my side in topic of application of geospatial technology in drought, where I just simply touch upon the part of its background side, then its definitions, its type, its impact, its causes, followed by the conventional approach, and then further how we can use geospatial technology, remote sensing GIS, and what kind of different kind of with or support of number of case study as I go through, and give you a practical understanding about how we can assess such kind of, you can say, calculation and computation for the assessment and monitoring of agriculture drought. So this is all from my side. Thank you very much. Okay, so thank you for your positive response. As I see number of queries in my chat box from our office side that you said studio. So few, as I define number of queries which are related to this particular topic of agriculture drought. So I just try to give the you can say suitable answer for the same. So one by one, I just taken up the questions and discuss with you about this particular, as you just have now a detailed idea about this particular topic. So very first, as participants ask, how can drought affect human health? It is not directly correlated with respect to human health part. It is a drought defined in terms of your, you can say, in case of our agriculture is defined the crop yield and crop growth. So which ultimately measurable in the crop yield side and which affect that you can say the economy of that you can say rural India. So in that aspects we can say it's a more related in not in terms of directly human health side. Next question is why are both NIR and red band used together to assess plant health instead of using only one band? Yeah, we can use one band also, but one band give you can say one directional information. It kind of that. If you integrate NIR band and red band, because in healthy and stress plant there is a significant variations in the reflectance of NIR band and red band. If we change, if we understand the change in you can say NIR band and red band with respect to healthy or stress vegetation and integrate and generate a speculation indices, then only we can create a significant informations about its variability. So likewise we can analyze it. One participant asked, with climate change increasing the frequency of drought, do you think geospatial technology can eventually predict drought early enough to completely prevent agricultural losses? Yes, it can assess a prior. The accuracy may vary with respect to that when we define it's a localized scale. Otherwise, we can predict, and also definitely that climate change impact on the part of frequency of drought. More you can say the severe impact of climate change is more you can say recurrence of drought in number of areas specific. One participants ask, what will be impact on VCI value as today hills has been destroyed? The basically the VCI calculation as we define based on the NDY value for agricultural landscape only. So if the agricultural landscape area or agriculture area, agriculture uh, you can say agriculture mask area or crop area, if it has the substantial change in terms of NDA value, then only in reflecting the VCI value and that we can analyze as a agriculture drought conditions. NADAMS, one participant asked why was NADAMS developed and what problem does it solve for agriculture. NADAMS basically a national agriculture drought assessment and monitoring system which is primarily developed to assess and monitor the agricultural drought conditions. Yes, currently MNCFC are taking care about the NADAMS project and on their website also, if you can search it out, MNCFC website, Manlabis National Crop Forecasting Center website, and on the website you can search it out about the agriculture drought status, the rainfall pattern, SPI, and more specifically the district and block level the drought conditions, so that you can easily assess, and on the basis of that information only that agro advisory services incubate the informations of the drought for a larger farmers population. One participant asked, how does NADAMS provide near real-time drought informations? As NADAMS include the near real-time remote sensing data sets with respect to ground observed data set, then that's why, and then only it's define a near real-time drought information, and based on that advisory informations may communicate to farmers. One participant asked, how is binary VCA maps generated from original VCA data? As your original VCA data sets are 0 to 50, you can use any kind of GIS platform and define just a conditions. If your VCA value is less than 50, make it 1, and rest of the data set where your pixel value in the raster image is more than 50, make it 0. So likewise, in very easy manner, using any kind of GIS platform, maybe you can say the commercial or freely available, you can use it and you can convert it as, you can say, VCA binary maps. One participant asked why western part are more drought than eastern part. Basically, it is not in terms of western eastern. It is basically because of that agroclimatic zone of the particular area specific, and which is simply defined based on the rainfall, soil, and length of growing period. So if the rainfall pattern is so, the rainfall availability is less in the particular area. So definitely the drought episode may be more in that particular area where erratic rainfall pattern may be there, less rainfall may be received over the time. One participant asked, since each drought indicators represent a different environmental process, how does the AHP does weighing system ensure that no single indicator disproportionately influences the final drought? It is basically just to integration of different kind of you can say the indicators or variables which may derive different kind of satellite data sets on platform, basically just to cater all sort of information which may not be covered up by the one satellite data and its informative you can say states, so that we consider with a integration. And definitely the weightage is based on AHP, because in AHP, as you define your weightage, I previously defined in class also, like it is based on your disease, you can say the expert advice, it is based on, you can say, subject specialist, it is based on the review of literature, like priorly people already did and they define it, or the questionnaires in the area specific farmers, and based on that you may define the pairwise metrics which variable have the higher importance. And once you define in the AHP the higher weightage, where you can say your CR value is less than 0.1, or you can say the percentage is 10%, less than 10%, then only that weightage is acceptable, and that is you can say applicable for a calculation in a MCDM AHV based process. One question is, since drought affects rainfall, vegetation health, soil moisture, and water resource differently over time, how does the trigger 2 matrix ensure a balanced and reliable assessment of the drought intensity? The drought intensity basically not, as we already defined, there is a four indicators, impact indicators are there. There is also in particular each and every indicator like soil moisture, then hydrology and remote sensing or agriculture, along with this, as I define in the table, along with other indices are also there, parameters also there, and their scaling factors is also involved in calculation to define the drought intensity for a larger area. If the condition is in between severe to even moderate also, then only they go for that final field verification, is the condition is actually at the farm is on the moderate, or the in a larger area or the village level in the moderate or the severe. So normal conditions may not be, you can say, entertained for the same, but for even the moderate conditions or severe condition is, you can say, in detailed manner examined by at, you can say, sample survey uh, through, you can say, ground truthing exercise. One question, how is the CDI validated against actual crop yield anomaly? And what level of agreement is typically observed. The CDI, the combined drought index, basically the mean value is defined in the calculations, while the crop yield anomaly calculated based on the detrend part, detrending. You simply, if you simply search it out, number of publications are there which define how we can do detrend the yield. Basically, you simply detrending, it means you simply remove the impact of mechanical, or you can say the technical upliftment in your crop yield part. So basically you simply detrend that part over that, you can say, historical and long term crop yield data sets. So that is the detrending. Number of publications are there, reports are there which clearly defined about the detrending. That crop yield anomaly which is after the detrending we include in correlation with respect to CDI values. Okay, so these all are the questions. So thank you from my side. You just wait for a couple of minutes for the next lecture. Thank you.
Hello and welcome to this particular uh, course on climate change induced disasters. Today I'll be talking on the remote sensing application for hydrological hazards. My name is C.M. Bhatt and I'm working as scientist in Indian Institute of Remote Sensing Disaster Management Studies Department. So when we say hydrological hazard, so hydrological, as we all understand that it is related to water, especially its movement, distribution, and properties on Earth, such as rivers, rainfall, and groundwater. And when we say hazard, we mean that it is a potential or threat that can cause harm, damage, or risk to people, property, or the environment. And when we put both together, hydrological hazards, they are natural events primarily caused by extreme hydrological processes such as heavy rainfall, snow melt, or a dam failure. Now, there are different classifications of hazards. Under natural hazards, there are various, as you can see from the table, geological, hydrological, meteorological, climatological, biological, and then there are environmental hazards, technological hazards, socio-natural hazards. So hydrological, as you can see, it is associated with water movements, and examples are floods, flash floods, storm surge, dam failures, and so on. Now, coming to types of hydrological hazards, there are flash floods, which are caused due to sudden, rapid, movement of water due to intense rainfall, or some, there can be also a dam failure. There are river floods every year happening, along the rivers due to high flow of high discharge of water into the channel. Coastal floods that may happen due to the cyclogenesis and the landfall that brings a lot of water and storm surges or sea level rise. There can be glacial lake outburst floods, that is sudden release of water from glacial lakes, mud flows and debris flow. They are also triggered due to the water saturated soil, rocks and debris moving downhill rapidly, and droughts, long periods of unusually low rainfall that leads to the shortage of water. Now, once we think of any disaster, there are various types of information that are required, about the location, what could be the probable cause, what is the extent, what is the severity, what is the persistence, at what elevation, or what was the soil moisture, or what type of precipitation, whether it will reoccur, any changes in the river morphology, what is the risk, and so on, and also the damage assessment. So the information required is very large, in terms of our data sets, also in terms of spatial extent, because these disasters have a regional footprint, and the time, if we say, it is limited, and the terrain can be accessible due to these hydrological hazards, and you have limited resources, and there can be collapse communication and damage instruments. So under such scenario, what the role of remote sensing satellites and becomes very important in the case of hydrological hazards. I know, because they have a global coverage. They can provide synoptic coverage. They can cover inaccessible areas. They provide us the pre and the post images, which are very important to understand what was there before and what has happened after the event has happened. Temporally monitoring is also required, because we need to see how the particular event is unfolding, how the dynamics of the water is changing. And above all weather conditions is also the capability of these satellites, because in monsoons or in adverse conditions, we may have a poor visibility, but under the some satellites are capable of viewing the earth in all weather conditions, and they are also not prone to damage, unlike the instruments which are on the ground, which can be washed away, or may suffer damage in terms of very severe events. So as you can see in the particular slides, so we have different types of now platforms, where we can get information from satellites, from aircrafts, from drones, and different types of sensors working in active and the passive mode, and different orbits. Now, coming to the various types of sensors that are available, we have the optical sensors, which are measuring the reflected light, thermal infrared sensors, which measure emitted heat or thermal radiation, passive microwave sensors, which measure natural microwave emission from Earth, especially they measure the brightness, temperature, or the soil moisture. Active microwave SAR. This is very useful in during hydrological hazards, which measures the reflected signal, that is a backscatter. We also have radar altimeters, which measure surface height, by computing the travel time of the radar pulse, and give us very important information on the sea surface height, or the water level, water surface elevation. Digital elevation model, we are all aware of different digital elevation models, from shuttle radar topographic mission, SRTM. Cartoset is a very popular Indian stereo product that provides elevation data, and this is very useful for delineating the watershed, and in all kind of hydrological models, this input is very much needed to have the floodplain, how the floodplain is, how the elevations are varying. And recently, machine learning and AI methods, they are not directly the form of sensors, but they help us to see the patterns, and how the things are happening under each pixel, and then allow us to produce maps of the vulnerability, or the and hazard prediction. So as you can see, there are a variety of sensors available in different domains, and many of them we are very much aware also, like the Sentinel-2, the Resource-2 from the Indian context, thermal sensors from Landsat 8, and actives are Sentinel-1, India's Reset-1. So they are various sensors. So we can see in various parts of the electromagnetic spectrum we have the capability. But among all of them, and this is just to show you how what parameters exactly these sensors help us to monitor. In case of floods, if you say, mapping of flood extent can be done, depth, duration, monitoring of the river discharge, rainfall, soil moisture, support for flood forecasting and damage assessment, droughts, monitoring vegetation stress, soil moisture and evapotranspiration, estimating rainfall deficits, water availability, assessing agriculture drought impacts. In case of landslides, identifying susceptible zones through slope, soil moisture and land cover, detecting the pre and post event terrain changes. In case of GLOFs, monitoring glacier retreat and lake expansion, detecting potential breach points, early warning through temporal image analysis. For case of coastal flood or storm surges, right from the cyclogenesis, tracking cyclone paths, wind speeds, rainfall intensity, and subsequently after the landfall for the mapping of inundation zones and coastline changes. So these kind of different dimensions or different kind of requirements can be fulfilled by these sensors. Now, just to give you a glimpse of the optical and the microwave sensors, these are more widely used in case of hydrological hazards. On the left, you can see the optical image, and the right, you can see in the microwave image. Optical sensors, because of their shorter wavelength, and working in the visible wavelength, their visibility gets restricted due to the presence of the cloud. They measure the amount of solar radiation reflected from the water surface at different wavelength, blue, green, red, that way. But they have the limitation that cloud obstructs their visibility. Whereas in the microwave, because of the longer wavelength, they measure the microwave energy that is backscattered from the earth's surface. Once the radar emits a pulse, it receives the backscattered energy from the surface, and therefore, because of the longer wavelength, they are able to penetrate the cloud, and they are not influenced by the ongoing adverse weather conditions, rainfall or haze. So, and therefore they are able to detect the presence of the footprint of the disaster on the ground. Thermal sensors are also, they can also provide you information, because they measure the thermal energy, that is long wave infrared radiation naturally emitted by the earth's surface due to its temperature. But they are more suitable in case of when you have semi-arid or dry conditions, where the conditions, you have a clear contrast between the diurnal temperatures of the day and night. So in those conditions, but in the case of where these temperatures are not very much distinct, or in wet conditions, they are not so suitable, and they are also have the limitation of the cloud cover, and therefore they are, and the resolution is also coarser, so therefore they are not so much used for mapping of hydrological hazards. We have passive sensors, also passive micro sensors. They measure the natural microwave radiation, that is the brightness temperature emitted by the earth's surface and atmosphere, without, they do not send their signal, but the emitted radiation, they receive this radiation, and that the emitted radiation varies with the physical temperature and dielectric properties of the target. But since their resolution is coarse, they are not hindered by the presence of cloud, but since their resolution is coarse, they are used at a regional level, to have an idea of how the soil moisture, or how the brightness temperature are varying, because the moment the land gets submerged by water, the contrast is captured in terms of drop in the temperatures, and there are various indexes also, where this differentiation can be captured. But however, because of the coarse resolution, they are not used actively as compared to your active SAR sensors. which have a very which have a better spatial resolution. But however, they have a very high temporal frequency. You have everyday passes are available, ascending and descending. You have two passes, so they can be used to monitor the event in a regional level, and to have an idea how the soil moistures and how the water are behaving, and how the things are getting evolved. So this I have already discussed. So now coming to actually what satellite basically provides us. When we say no satellite, so it provides us two types of information. One is the spatial extent, that is directly visible to our eye. Like on the bottom, you on the side, you can see that is a image, that is a false color image, and that is has captured a flood event that has occurred in somewhere in the month of September 15 over Assam. So by looking at the image, we are able to see that there is a flood event, and if we are acquainted with GIS, we can map the boundary and have the extent of the flood. So that is one form of information that we can have. But the other information is that these satellites are also used to validate and calibrate your hydrological models. So if someone is in the hydrological modeling part, so the information derived from the satellites can be integrated with flood models, via model calibration or validation and data assimilation techniques. And they also can provide floodplain topography data to augment the amount and type of information, so available for efficient flood management. So two ways, to validate your hydrological modeled outputs, and also have a direct extent of this, they can be used. Now, how this is done, in case of optical sensors, they are acquiring information at in different wavelengths, visible domain, then NIR, and SWIR. So, if you see this particular diagram, you can see in the visible, as for water, in as it goes in the NIR and the SWIR, the water is the reflectance goes down. It gets the signal gets completely absorbed by the water, whereas for the vegetation, it is in contrast. In NIR range, vegetation has a very high reflectance as compared to water. So this contrast is made use basically to distinguish between land and water. And subsequently, the just this is example where you can see green and swir band. Green, if you see the image on the left, you are not able to distinguish water very clearly, because it has a higher reflectance in this particular wavelength. And once you go to the right image, you are able to see that the channels on the top, and the areas which have are darker, they have a presence of high water or moisture because of the rainfall activity, or maybe because of flood. So you are able to distinguish the presence of water in a much better manner compared to a green band. So that is what this diagram was reflecting in the NIR and the further higher infrared part of the spectrum. The it gets completely absorbed, and that is why it is appearing darker. And once you combine different bands, three bands, we also are able to produce a false color composite by taking green, red, NIR, or different combinations. We can have we can exploit the properties of all bands, and make the interpretation much more better. Like in this example, you can see there are four circles put, and in all four circles, if you see there are tonal changes. The color getting that of the water is different. If you see on the right top, the water is very dark bluish in nature. That means it is a calm water, deep water. If you come down on the right side circle, it is, you have a very greenish, or that kind of tone is appearing, so that it is a fresh wave of flood. So a lot of sediments are in the agitated form, and that is why this represents that it is a fresh flood happening. And if you go on the left side top circle, you are able to see some bluish and greenish tone, which shows that it is a relatively older flooding, and the water is trying to settle down, and and but presence of water is there. And if you come on the left, on the bottom, it is a carbon black kind of color where the water has been completely absorbed by the ground or evaporated, but so it has become the tone has changed. So based upon the tonal changes, we can interpret how at what stages of flooding these particular locations represents, and accordingly, we can model, use different modeling or different classification techniques. This is what I was trying to tell. This we were seeing a false color composite, but in this image this is a different kind of combination. You can have a natural color, you can have different kind of combination. So if you see the images on the left, it is September 19 image where the water is in a calm state. And if you see subsequently on the right side, that is a different date image. In that you can see there is a little turbulence in water, and the same image has been put down in a different combination where you see a lot of muddiness in the water, so if you so by making use of different bands, like in this case red, near infrared and short wave infrared bands 543, so it helps us to make it easier to distinguish between water that is dark blue and vegetation green. Water with more suspended sediments appear lighter blue on the top image, and similarly, that is a down one is a different combination where suspended sediment looks brown in the natural color version of the same image below. So that is a natural color composite, NCC. Our visa, 543 have been used. So by using different bands of combinations also, we can make the interpretation more relevant as per our requirement. Now, coming to there is one more form that we spoke earlier, that is the active microwave. That is the SAR remote sensing or synthetic aperture radar remote sensing, where a pulse is transmitted by the satellite, and depending upon the ground conditions, it is reflected back or backscattered echo is collected by the receiver. And how the signal will be backscattered, it depends upon radar, that is the parameters of the satellite, like frequency or the wavelength, polarization, incidence angle, and the surface parameters. What is the roughness, terrain, relief, or the viewing geometry, and the dielectric properties. If you see the second image on the left side, you can see there, see we have different types of wavelengths that we use in active remote sensing, like X band, C band, L band, S band, P band. So you can see from X band to L band, the wavelengths are increasing from 3 centimeter to 23 centimeter. As the wavelength increases, the penetration also of the the signal increases. So first, if you see first picture, the in the signal is not able to penetrate and is coming reflected from the backscatter from the top of the tree. But C band you have a moderate penetration, and the L band you have a higher penetration. So that is where the role of the these bands come into picture. So their wavelengths role come into picture. And down you can see the polarization. How how the pulse is sent and how the pulse is received, whether it is sent in the HH horizontal polarization and it is received in the horizontal polarization, it is a HH, and it is sent in the horizontal and received in the vertical, it is a HV polarization. So these they can have HH, VV, HV, VH. So it is a chord, we can have chord pole kind of data. Then in the bottom right side you can see, depending on the surface properties, if it is a very smooth surface, you have a specular reflection. That means the water comes and interacts with the surface and goes away from the receiver. And if it is a rough surface, you may have a diffuse kind of backscattering. And if it is a where you have tree stem, or it in the case of urban areas, you may have double bounce. The signal first goes away and again it is meets some stem or tree and goes back to the receiver, and the backscatter gets enhanced. So these are some of the properties on the surface which affect. Apart from that, incidence angle also plays a role. How the incoming signal, how it makes the angle with the perpendicular on the ground. And if you have shallow incidence angle or steeper incidence angle, that also influence the interpretation of how the signal will interact with the water or the vegetation. So now how we use this information for remote sensing. Basically we are using remote sensing for four kind of cases. One is response phase for any kind of hydrological hazards. I have taken flood management, flood especially because floods are more common in we see hydrological hazards. So it is a response phase where the moment any disaster occurs, how the satellite has observed the area, that is the products derived from the satellite. Then you have a post disaster. Once the disaster has happened, we are mapping the damages or the shifts in the embankments or the river course. That is a post disaster for relief and rescue operations. And the third is the mitigation phase, where we are trying to have a hazard zonation map. So trying to identify the areas which are vulnerable. And there is a warning phase, where we, based upon the hydrological simulations or other kind of analysis, we are trying to predict the areas which could be impacted under certain scenario. So this is one example. It is a active microwave SAR data, which shows you how the temporally the floods are evolving in parts of Bihar, and it is a river Ganga. And you can see in dry periods the entire image looks to be of white, except and in the gray contrast, and the river appears to be in the black contrast. But as the flood progresses, you are seeing the black portion to enhance or increase, because it is appearing black, as I told you, because of specular reflections. The signal does not go back to the receiver, and there is no energy received by the sensor, once the pulse is transmitted from the surface of water, and therefore it has a low response or low backscatter, and therefore it has a black tone. And whereas the other areas which are appearing in moderate or brighter tones, so they may have a diffused or they may have a stronger backscatter return. So this is one example of of the map on the bottom side. It is a flood persistence map based upon a number of images. We have tried to represent which areas are underwater for different duration of time. Say for pink color under 4 days, green areas are for 10 days, and red areas are more than 2 weeks underwater. So the severity gets delineated, and accordingly we can have our mitigation plans. If we have high resolution satellite data, we can map individual buildings or footprints of the building where the water has entered and which areas are impacted. As you can see in this image, it is 0.65 meter, roughly, of data, where you can see each individual houses, and and the roads, and the muddy water which has flooded the area. Similarly, we can use satellites in case of floods for creating flood hazard zonation maps, like our center at National Remote Sensing Center. They are proactively mapping the nationwide floods, once the flood season starts, and they have been doing this for more than of 2 decades now. So they have vast information about the areas which get regularly flooded. So they have created, they flood hazard zonation maps are created, and which tell you the frequency of each pixel, how frequently it gets flooded, and based upon that, these maps are generated. As you can see, the pink color shows that it is a high frequency, that it gets flooded every year. If you have taken data of 20 years, so out of 20 years this may be flooded 18 to 20 times. So those areas, we need to have a different kind of planning than areas which are less flooded, or low rate of flooding, which are where we are observing. So this information now, once from the satellite we have the flood hazard, we can extract the extent of the flood, we can extract the land use from the satellite images, and we, in our GIS, we have the administrative boundaries like villages, roads. We can integrate to find out the villages submerged, flood duration, flood persistence, land use affected, flood depth. So all this kind of information can be derived once you have the basic input of the flood hazard extent. Another one sensor I was talking, among those sensors which we discussed earlier, one sensor was that altimeters. Now altimeters are also playing a very efficient role these days in terms of hydrological, for deriving hydrological parameters. This satellite altimetry, is useful in studying river discharge and river reservoir volume, which can be used for calibration and validation of hydrological, hydrological and hydraulic models, rating curves, stage discharge relationship, near real-time flood forecasting, reservoir operations, and transboundary related issues. So how basically it works, this is the typical, on the right side you can see altimetry satellite, it sends a pulse that is in the red color and receives the echoes reflected from the water surface, and these are received with an accuracy of few centimeters, and water level can be derived by the changes, as the water increases, so that the travel time also will change. And so these can be done, and there are now a number of missions like Saral Altica, there are Jason, Topax, earlier Topax, now we have the SWOT mission, surface water oceanographic ocean or topographic mission, that is very useful, and that allows you to have a water surface elevation in a spatial context. Flood depth is also an important parameter which can be derived, conventionally. How it is derived is, by using a flood polygons. You integrate them with digital elevation model, and you get the elevation of flood polygon boundaries. Then we generate a surface of this, and flood polygon. Then we have a flood polygon service, and we subtract both, and we get a flood depth map. As you can see on the left side also, it is demonstrated, we have a pre-water level of 92, and then the river has risen to 100 meter, and once we subtract these two, we get a difference of 5 meter. So why this, and this is a basic concept that is used inside in all the hydrological, or whatever softwares we are using to estimate the depth. And on the right side you can see why the depth is important. If we satellite can only tell us the extent of flooding, it will for it everything is flood, but among that flood, which are the areas which have higher level of depth, and which require more attention. So like in this picture you can see there is 70% of area which is less than 1 meter, but only 12% of area which has more than 2 meter or 1 to 2 meter, so the areas which is having 12% of area more than 2 meter, that means that is more critical than focusing on the 70% area which is less than 1 meter. So depth can help you to classify those areas which have higher problems. So depth is more important. This is one of the slides that I was trying to tell you about the surface water and ocean topographic SWOT mission. So this is also an altimeter, but altimeter mission, but this is not another. This is more of it gives you a spatial continuous raster based kind of product you can generate. At each pixel you can get the water surface elevation, unlike your conventional altimeters which only tell you at that particular point where they have a pass over the river. So these are now becoming more popular, and many of them, many studies are emerging, and this is one of the study that we also did to find out how the water level has starts rising. So you can, so now once you have you have digital elevation model, you have those sensors, optical sensors, microwave sensors. So you can also go for flood hazard simulation, by using land use, different kind of meteorological data inputs, by extracting your river profile from the satellite data, and then taking it to the model by using different models like HECRAS. You can generate your flood depth, watershed boundary, by, so all this you can use to generate create your flood hazard simulation. And this is one of the example that how discharges at different discharges, what could be the extent of inundation, this could be done, and the results can be calibrated and validated by using different satellite data and the ground observation from the gauge levels. And now these days altimeters can also help to validate the water levels. So this is one of the study that we did for Sabri area, where we did used optical satellite for driving the land use and deriving the channel conditions and hydrological data and satellite micro data to map and validate the model output. So this is one of the example where satellites can be used in case of landslides. Hydrological, landslide also get triggered due to the presence of excess rain. They loosen the soil and they trigger the movement like debris flow and all that. So satellites can help you to map the extent of the submergence, the nature of the landslide, what is the area that landslide has, that where the material has been removed. You can visualize it in a 3D environment. You can also create a depth map, how much depth, how much the water has. And also studies can be done to estimate the volume of sediments that has been deposited in the river course, so that what would be the nature of blockage, how much the water level, and subsequently modeling can also be done to observe how much upstream water will be accumulated in such conditions. Now coming to one more aspect, it's snow and glacier also. Snow and like gloves and those kind of disasters are also triggered. In this. So snow has a very high reflectance, as you can see in this particular diagram. In the visible wavelength region, and a considerable low reflectance. It has a in NIR and mid and shortwave infrared region. It has a low reflectance, and in visible it has a very high reflectance. This property is made use of the reflectivity of, and also we can distinguish between the freshly fallen snow and the old snow. So different kind of snows also can be distinguished based upon their reflectance patterns. Dirty glacier ice, or refreezing ice, or glacier ice, fresh snow. So based upon these, using these properties, the extent how the glaciers are receding, their geomorphological nature, all those can be mapped, and also can be used to map the snow cover dynamics. How the snow cover is has changed. And these are very important. Mapping and monitoring of snow dynamics is very important, in weather and hydrological forecast. They become very important input. So satellite allows us, because it is very difficult to access these areas in during high altitude areas, whereas satellites can easily do that. This is one example of South Lunar Lake, where multi-temporal satellites have been used to see what actually triggered that those flash floods, how the moraine got collapsed, and how the conditions of the lake changed, from frozen state to floating of ice sediments, and how the volume of water changed. So all these can be observed. So in this case, when the area is cloud free, the optical sensors are very they provide you very accurate information. And so in this case optical satellites have been used. You can also use for avalanches, that are triggered in case of presence of the snow. Avalanche deposit can be easily distinguished from the old avalanche, new avalanches, based upon in this both optical and SAR can be exploited, because of their roughness. Older avalanche appears darker than the new one in the SAR image. And the fresh avalanche brightness of radar image varies based on the roughness of the surface and how moisture it contains. So rougher surface and those with low water content will appear brighter. So you can see in the right image the fresh avalanche, because it is a rougher surface. You will have a more brightness. Similarly, in the optical also you can distinguish between the old avalanches and the fresh avalanches. So these help you to map the avalanches also, and subsequently We can also do modeling and simulation or vulnerability mapping of the avalanche prone areas using GIS and various kind of inputs from the digital elevation model, like the slope, elevation, aspect, curvature, then land use map, and based upon certain conditions which trigger by giving them weightages, we can find out and also do certain kind of modeling. So this is one of the event of Chamoli rockfall that happened in 2021, where satellites have helped to capture, as the event was unfolding, satellites were passing over the area. So you can see on the left image, that is on 7th February 2021, where you can see the plume of the dust because of the release of the sediments, or the a big huge mass that got removed on the top, and it rolled down, and that which generated all this kind of dust plume. So that can be captured. And the right side, after the event, once the dust and all that sediments got settled, you can see the valley. So digital elevation model helped, has helped to find out, assess what is the kind of volume of material that came down, rolling down to the valley. So roughly we estimated 23 million cubic meters of volume of material got dislodged. And this was possible because of the Pleiades stereo satellites. Because of the DM, if you have the pre-DM and the post-event DM, you can assess how much thickness or how much the volume of the material came down. Hydrodynamic simulations can be done in case of hydrological disasters. If you have the as earlier I have shown one example. This is one example where for Joshimat, that event, how much volume of water will travel down, what will be the velocity, what would be the depth, and what would be the extent. Such those kind of scenarios also can be assessed. In case of cyclonic hazards, satellites help us to measure the cloud top. Temperature measurement can be done. Cyclone intensity estimation can be done. Cyclone eye detection, storm structure analysis, tracking movement, and right from the cyclogenesis to the landfall, lot of control our satellites have given for studying the satellites. And that is why we see these days, we are able to forecast exactly where the landfall will happen. Roughly 7 to 10 days in advance, we are able to predict, and we are able to minimize the losses that earlier were happening. Similarly, for drought monitoring, which is also one of the hydrological, like in this case also, we can see the stress in the vegetation, how the NDVI is changing, how the soil moisture is changing, the rate of evapotranspiration. So all those factors, different factors can be taken from the satellite-based products, and their anomaly can be detected, and we can come out by using certain drought indexes. We can do the drought classification can be done. So this is in general, this is in general what I was trying to tell you about the entire nature of the role of remote sensing satellites for hydrological hazards. So I can summarize that in satellites can play a very important role, especially in case of hydrological hazards. They are playing a very critical role in providing information to the decision makers, as well as to the researchers to study the nature of the phenomena. Thank you.